Okay, good morning, good afternoon, wherever you may be. Thank you for joining us for this education session. So continuing on with the agenda then is in the appendix, and we won't have time to go over this, but it's really more for your reference, is some of the common configuration statements that Lifeline provides, and we have a manual for out on our website for Multi-site Workload Lifeline that also contains more detailed information about these statements. So first, what is Multi-site Workload Lifeline? Well, it's a product that provides two benefits. Really, it plays a key role in solving two problems that a lot of the enterprise customers have. One is for your critical workloads, being able to have continuous availability. Having, with 24/7 now with, in banking applications or, web-based stores, they always need to be available all the time. So if there's any type of outage, you can't afford a 4 to 6 hour downtime while you're trying to recover your workload to another site. So for some of these specific critical workloads, you need to have this continuous availability feature. The other thing is for downtime during planned outages. Everybody always has planned outages, either for putting maintenance on, maybe making application upgrades, maybe having to do some type of power on reset of your data center. During that time, you have downtime, and you're constantly trying to minimize that as well. So first of all, what it does then is for the continuous availability aspect of it, Lifeline enables the intelligent load balancing of workloads across two sites at unlimited distances. So what this gives you is increased performance. So what you have is your client transactions, you're going to have a reduced response time, because we will ensure that any transactions for a workload get distributed to the applications and the systems that have the most capability of handling them. You get increased availability so that within a specific data center, we can route around failed systems or failed applications to applications that can handle the work. In the event of an entire outage of your workload on that site, either the workload completely failed or the site failed, we have the ability to route around that site and go to a remote site. We also have increased scalability, and what that means is just during peak times, you could add an application on demand, an application instance for this workload on demand, and we'll automatically be able to start routing to it to help alleviate any type of bottlenecks you may have. Analytic capability, we provide a network management interface for this Lifeline product. And what it does, it allows any type of network management applications to retrieve information about all the workloads, the statuses of the workloads, the health and status of all the applications, as well as the status of the sites and all the systems that make up both of the sites. And finally, what it does is it improves your recovery time. This recovery time objective, or RTO, typically in a disaster recovery, especially across large distances, we're talking several hours to be able to, at least several hours to recover to the other site. With this Lifeline product, as well as when we're talking about this GDPS active solution, we can reduce that time down to minutes. All right, now from the graceful movement standpoint, what Lifeline also provides is the ability to move workloads from one site to another gracefully. What that means is you don't have to have an outage in order to have this workload switch from one site to the other. We can gracefully move the workload without any data loss and minimal disruption to another site. So what this allows for is a workload migration. You can move that workload from one site to the other during times of planned outages, or if you just want to move the workload to the other site for availability, there may be more resources on that other site at this point. Increased availability. So when you do have these planned outages for maintenance upgrades or any other type of planned events, the outage time can be minimized, which means that your critical workloads are more likely to be available. And finally, a lot of customers now are having to actually verify their disaster recovery procedures. And what I mean by that is they need to show that their workloads can actually run on their disaster recovery site. This, again, is somewhat a disruptive process for customers to basically have to bring down their other system, their one site, possibly either move IP addresses from that site over to the remote site, or somehow change their networking infrastructure so that they can actually route to this alternate site just to show that their workload is able to be run on this alternate site. And typically they do not want to then move it back to their production site until either the next planned outage, because it does take a hit on your recovery time. So with Multi-site Workload Lifeline, we actually can minimize that as well. We can easily move that and gracefully move that workload over to another site. You'll be able to verify that the workload is being able to run on that other site, and then gracefully move it back if need be. We'll talk about that a little bit more. All right. So first, continuous availability. For those of you who are familiar with GDPS, Geographically Dispersed Parallel Sysplex, there's a couple of solutions that rely on disk-based replication. They've been out there for 10 or 15 years now. One of them is PPRC or Metro Mirror. And essentially what that is it's a synchronous disk-based replication product or solution. So what that means is any type of I/O that is done within a data center to a disk gets replicated remotely and synchronously to another site, so that if you lose this specific site, you can switch over to the other site pretty quickly. The limitations is that this is really a single parallel sysplex, which means that the distance between these two sites cannot be more than tens of kilometers. Otherwise, the latency that involved with access to the coupling facility, et cetera, would be too great, and it starts to impact your workload and your transaction response times. So you do get a low recovery time, and you get zero data loss because you're doing the synchronous replication. But a lot of times, and especially after 9/11, customers are being told to actually have their workloads or their data centers separated by further than metropolitan distance, so that if a metropolitan-wide disaster occurred, you could still recover to a remote site. So although this works very well, it does have some limitations in the sense of our distance limitations. So the other solution that GDPS provides for disk-based replication is called XRC for Extended Remote Copy, or GM for Global Mirror. And in that scenario, there really is two distinct sysplexes. It's no longer a sysplex that's just spread across a local distance. These are two distinct sysplexes, and we use asynchronous disk replication. With asynchronous disk replication, that means you will have some data loss during a disaster, but it's usually on the order of seconds of data loss. But what it does is provides for recovery for metropolitan-wide disasters, so that you would have a data center on a remote site, and you could recover there. One of the limitations with this solution is that it's a longer RTO or recovery time objective. The reason being is that other site is a dark site. Because you're doing disk-based replication, the data is not available on that other site. So what that means is that only when you have a disaster, you can bring up this other remote site and then actually start using that data. And again, this may take on the order of hours to get the sites up, get the subsystems up, put any networking changes involved so that you can go to this remote site. And as we mentioned, customers, for their business-critical workloads, having an RTO of hours may not be acceptable. They want to be able to have it on the order of seconds or minutes. All right. So that brings us to the active sites. So what is active sites? This is actually a solution that we GA'd in June of 2011. There's different iterations of it, and we'll get into what those are. But essentially what it is, it's a solution to provide continuous availability for business-critical workloads. This is not intended to recover every workload that's running in your data center. For the other workloads that are running in your data center, you would still rely on your GDPS PPRC or your GDPS Global Mirror solutions to do that. What this is geared toward is just identifying which workloads are business critical and use GDPS Active to provide this continuous availability for these workloads. So it's kind of a paradigm shift from this failover model, which existing disaster recovery solutions have, to a near continuous availability model. And as you notice, there's several components of it. One of them is rather than using disk-based replication, we are now using software-based replication, software data-based replication. We'll get a little bit of that in a subsequent chart. So the software replication is really used to keep both sites in sync. And we also have this controller on your lower right-hand side, and that's really responsible for managing all of this, which means that managing where workloads are running, which workloads run active on one site versus workloads that run active on another site, as well as retrieve any type of metrics that are needed just to show how the overall workloads are behaving. And in the center of the picture is this workload distributor, and this is really what we'll be focusing on in this presentation here. This is where the Multi-site Workload Lifeline resides, and its responsibility is for routing workloads between these sites. So if we go to the next slide, then on page 11, there's two different configurations right now. The one that we GA'd on 2011 is called ActiveStandby. We'll show an example of that. And we gave a statement of direction for ActiveQuery, and we'll show that as well. But the key thing here is a configuration is specified on a workload basis. So with disk-based replication, it's an all or nothing thing. You recover all the data in a site, and you recover it to a remote site. With active site, you actually, on a workload by workload basis, you say you identify which workloads you want continuous availability for, and we will only replicate the data for that workload over to the other side. So what is a workload? It's really it's made up of three components. It's a software. For example, it may be a COBOL program running in a CICS region, and that COBOL program is accessing a DB2 subsystem. So in that case, that's all the software that makes up that workload. The data is really what pieces of data does that workload update or access. And that's a key thing here because, for example, if you have one application writing to a specific DB2 table and then an entirely different application also accessing that same DB2 table, even though they're distinct applications, they really belong in the same workload because they're both accessing the same data. Whereas if you have a workload that is updating, say, DB2 and a workload that's updating IMS, you would define those as separate workloads. So that way we can take recovery actions based on a workload by workload basis. And finally, the third component of a workload is network connectivity. It's really how do you reach those applications. So for example, if you have a CICS region that has an HTTP server, that's how you access it. Well, the network connectivity, how to get to that HTTP server in CICS, that's part of this workload definition as well. So here are just a couple of pictorials then on what these different configurations are. First is ActiveStandby. And what ActiveStandby is having a workload defined, and what we do is we will guarantee through the workload distributor that all transactions for that workload will only go to one site and one site only. The reason behind that is if you have a workload that can update a specific DB2 table going to both sites simultaneously, you can have data conflict. So what we need to do is ensure that all transactions for a workload only flow to one site at a time. So in this case here, the workload distributor is saying the active site for workload A is site 1, so all transactions go to site 1. Now we have data replication that will actually then, software-based data replication, that will take those updates that are applied in site 1 and send them over asynchronously to site 2, where they get applied there. So now if you go to the next slide, in the event of either a workload failure, if all the servers, for example, on workload A were to fail, or the site itself were to fail for some type of a disaster, at that point the workload distributor can then be notified of that and actually then route all workload transactions over to site 2. Since we had been doing software-based replication, the data is over there in the database is over there, so now we can basically pretty much switch over immediately to site 2 and be able to run workload A over there. Now, as part of this, as you probably see, both sites are active now, are up and running. It's different from the GDPS Global Mirror solution where the second site is dark. The second site here is actually up and running and capable of running workloads. So if we go to the next slide, in this example here, you can actually take advantage of that alternate site that is currently up. So you have workload A active as previously, and we direct all transactions for that workload over to site 1. The next slide you'll see, now we have another workload called workload B. In this case, since it's operating on different data and has a different set of applications, we can treat it differently in the GDPS active configuration. So we actually now say, well, workload B can be active on site B. So now we're actually using both sites for productive work, as well as both sites are doing data replication on behalf of each other, so that if workload A were to fail, we could route workload A and recover it over to site 2, or if site 2 were to fail, we could move the workload B over to site 1. So they're basically recovering for each other as well. Finally, ActiveQuery. This I mentioned is just a statement of direction when we announced ActiveStandby in 2011. Essentially what you have here is you still have your same ActiveStandby workload, And what we're doing here is workload A is an active standby workload, which means it's doing update transactions. So this workload is actually doing updates to these databases. So we need to ensure all these updates only go to one site. In this case, we go to site 1. Now suppose, if you go to the next slide, we have a workload B, and this is a query-only workload. It queries that exact same data that workload A was updating. In this case, since the data really exists on both sides, we can send these query transactions to either side. We don't have to worry about data conflict because we're not updating the data. So we can actually go to both sides simultaneously with different transactions to query the data. And what we'll actually use in this active query configuration is we'll actually monitor the data replication. Essentially, we call it the database replication latency, how long it takes for updates that are occurring in Site 1 to make it over in Site 2, and the workload distributor can take that into account on how it routes query transactions. So, for example, if the data on Site 2 is falling further and further behind due to replication delays, we may want the workload distributor to start favoring Site 1 more for these query requests because the data is getting stale on the second site. So this is more of kind of a dynamic routing of this workload B depending on the availability of the servers as well as how in sync these two databases are between the sites. All right, so going to the next slide. This is a very busy slide. I'm not going to spend too much time on it, but this is the overall GDPS active-active site structure. We have primary and backup controllers. For those familiar with GDPS disk-based replication solutions, this is kind of similar to the K systems that exist in those solutions. We also have Lifeline advisors running there, and we'll get into that a little bit more detail. We have this concept of multiple tiers of load balancers, and within each data center, we have agents, we have the databases, we have the capture and apply servers. These are really what are doing the database replication between the sites. So we have a lot of this stuff going on. But if you go to the next slide, basically what we are interested in is what's circled in blue. The Lifeline advisor that are running on the controllers, the first and second tier load balancers, and the Lifeline agents running in the data center. And this is what we'll spend most of our time talking about. So going to slide 20 then, what are some of the requirements that the GDPS active-active sites requires on load balancing? Obviously, the first one is being the ability to distribute workloads between sites. So what you want to do is have the ability to distribute connections to either Site 1 or to Site 2 without having to have any changes to the client. The client should be able to continue to send to the same destination, and then the decision is made on which site to go to. And as part of that, then if a site were to fail, we need the load balancing solution to be able to detect that workload or site failed and route around that failed workload or site. And how it determines if a workload or site fails, well, it's based on the capacity and health of the sites and the server applications for that workload within a site. So if there's no server applications running within a site, well, that workload is considered not running there, and it's a failed site for that workload. The other thing that we would need is the ability to switch workloads, gracefully switch workloads from one site to another. Basically, what this is useful for is if you actually have a failure and you have to switch over to the alternate site, eventually, if you bring that first site back up, you may want to move back to that site. So what we provide is a graceful way of moving back to that site, which was your original production site. The other thing that required of this load balancing solution is the ability to maintain this workload configuration state. And we'll show that in a minute, but essentially what we need to ensure, since this is a continuous availability solution, we need to ensure we have no single points of failure anywhere in this solution. So as part of that, this is where this bullet comes in about maintaining configuration states across peer workload managers. The other thing we need the ability to do is dynamically add and modify workloads. If you want to add a new workload to this GDPS active-active framework, you don't want to have to bring everything down and then bring everything up with this new configuration. So we need the ability to add and modify workloads on the fly without actually having to bring down all the infrastructure. And finally, as I mentioned, we surface all these routing recommendations that we make up to a network management agent, and in this case it's NetView, so that they can use their Tivoli Enterprise portal to basically graphically display what's going on. All right, so this is a prior slide, and what I've done here is it's similar, but I've stripped off everything that doesn't apply to Lifeline. And so what you see here is you see two Lifeline advisors, each one in a primary and a secondary controller, and they're running in distinct sites. These sites can be geographically large distance apart. We also have in each site a data center where there's server applications running, as well as a Lifeline agent running on each one of these LPARs within that data center. To the next slide, the first communication I wanted to talk about that what Lifeline does is there's an advisor to agent communication. The advisor has a list of all the workloads and all the server applications that make up that workload. And what it does is it communicates that information to each agent running on every LPAR across both sites. The agent's responsibility is to report back, is the server application for this workload available? Is it even healthy? That's a key part as well. It's not an all or nothing where the server's up or down. The server could be up, but it may not be accepting any connections now. So from our standpoint, that server is not available if he's not able to accept any new connections. Likewise, the Lifeline agent actually queries WLM, the workload manager, to see how much resources are available on this LPAR. So, for example, if a specific LPAR is really constrained for resources, then the agent may say, well, the server application isn't a good target to send to for this specific workload because we don't have enough resources to service the transaction. So the agents report all this information back to the advisor. If you hit enter or go to the next slide, the next thing is the advisor to LBs. And in this scenario here, what happens is based on the information the agents have given the advisor then goes out to this first tier load balancer and says, which site do you send transactions for this specific workload? So what happens then is if for a given workload, suppose site 1 is the active site for the workload, then the Lifeline advisor, when it communicates to the first tier load balancer, it will say any transactions or connections for this workload you need to direct to site 1. And it will actually direct it to the second tier load balancer. So in the second tier load balancer, its responsibility is once we're within this site, it picks which server application is best able to handle the workload request. So the first tier is responsible for figuring out which site to go to. The second tier is once we're within a site, which server application to send to. This first tier load balancer it requires to be something called a SASP-enabled load balancer. Citrix, F5, and Cisco all have load balancers that support this SASP or server application state protocol. Essentially what this protocol does, it allows a type of workload manager to give more detailed information about how to route among different servers. So in our case here, we're using SASP to tell the first tier load balancer which site to send a request to. You could also have a SASP-enabled load balancer as your second tier, in which case a Lifeline advisor will update that second tier load balancer to say, once we're within this site, which of these server applications is better able to handle the work. You could also have Sysplex Distributor be your second tier load balancer, and in this case, the Lifeline advisor does not need to send any recommendations. Sysplex Distributor can figure it all out by itself. The next flow is the advisor-to-advisor flow, and this goes to the point I was making about not having a single point of failure anywhere. In this case here, we have a Lifeline advisor running on the primary controller. It is the one advisor that's currently considered active in this solution. It is the one that's responsible for talking to all the Lifeline agents as well as talking to the different tiers of load balancers. As well, what it does is it maintains state information. For example, it knows which site a workload is active on. In one of our examples for ActiveStandby, I showed one workload could be active on one site and another workload could be active on another site. So the Lifeline advisor maintains a state of where all the workloads are running, whether they're active or not, as well as which site they're running on. He passes all that information over to the secondary controller, the Lifeline advisor on the secondary controller. In the event that the primary controller or the Lifeline advisor running on that primary controller were to go down, that secondary Lifeline advisor running in Site 2 would automatically take over and he would know all of the state information. all the first and second tier load balancers as well as all the Lifeline agents would automatically reconnect to this new Lifeline advisor running in another site. So you do not have a single point of failure in this case, since we've maintained state information across a failure. Okay, the next flow I wanted to talk about was advisor to SEs. These are the support elements that actually run on the hardware or the CEX within a data center. So if you have two different CEX where your sysplex is spread across, you would have two different support elements running in these. What the Lifeline advisor does, it is actually communicate with each support element over the HMC network to query status of the LPARs. Why this is important is in order for a Lifeline advisor to detect a site failure, it needs to actually go to the support element. If it can reach the support element and the support element says all the LPARs that make up this sysplex or this site are down, then from a Lifeline advisor perspective, that's a site failure, and he'll report a site failure. But he actually needs to communicate directly with the support element to get that information. Likewise, in this first flow, the advisor to agents flow, the advisor can communicate with the agents if he loses, if the server applications are no longer there, and so the agents report back there's no more server applications available for that workload. That's how the Lifeline advisor can detect a workload failure, and he will surface that up as well. So the support element communication is really for being able to detect site failures. And finally, the last flow I wanted to talk about was the NetView to advisor flow. This is for the NetView actually queries the advisor's NMI to get information about what the status of the workloads are. Basically, what site is the workload currently active on? What are the server applications that make up those workloads? And what are all the LPARs that make up a site? All of that information the advisor has, and he pushes all that information out to NetView. NetView then communicates with Tivoli Enterprise Portal and basically creates screenshots of all of this monitoring data. So that's the first use case of Lifeline is really within this GDPS active-active solution. The second case I wanted to talk about is graceful switching. Before I do that, I want to go a little bit more detail about what software data replication is. A lot of you are probably familiar with disk-based replication, where what you do is every I/O operation, write operation that happens to a disk gets replicated, usually asynchronously, to a remote site. What software-based replication is rather than replicating every I/O on that disk, what it will do is, based on a database by database level, it's a solution for copying data between the databases that are typically residing in different sites. So the key thing is rather than everything getting copied over, it's only selected information that's getting copied over. So from a replication standpoint, the scope is you could have an entire database be replicated, or if you have a lot of tables in your database and there's really only a subset of those tables that are used by your mission-critical workloads, then you only really need to replicate those tables. So what it does is it kind of lowers your network requirements across data centers if you're trying to copy every piece of data, when really all you need to copy is specific information for your critical workloads. And so why does customers, there's different replication products out there. There's from IBM. One of them is quite familiar is QRep or DB2 replication. I think it's now called IBM InfoSphere Data Replication, or IIDR. And the other one is IMS Database Replication. A lot of customers use these products today, and what they really use them for is that they have then this other copy of data residing in a remote site. Unlike disk-based replication, where that data is not available to be used at that time, it's not until you actually stop replication and then bring up those volumes and bring up the subsystem to read those volumes. With software-based database replication, that data is immediately available on the alternate site. So what you typically do then is you don't want to have updates occurring on that site as well. What you want is it to basically be a read-only database. And what it does is customers a lot of time use it for near real-time reporting. They may have some batch processes that just queries the data to get some real-time monitoring or metrics of the data. and they can use this query copy of the workload rather than trying to do these batch jobs on their production database. The thing they use it for, and what we just talked about in the prior slides, is for continuous availability. You can use this to replicate specific database tables for your business-critical workloads so that you can recover them from them during a disaster. Okay, so then going on to page 24, so like the GDPS continuous availability solution, there were certain requirements put on load balancing. Similar for Graceful Switch, there's certain requirements that are put on load balancing as well. Again, we need the ability to distribute workloads between sites. But rather than with GDPS Active, where we could automatically do the switching of the workloads, since we're doing graceful switching, we need the ability to have customer-driven commands influence how the distribution of workloads occurs or when we do the switch of a workload. And so what we also need then is the ability to gracefully switch workloads from one site to the other. Unlike the GDPS solution where we really only use this graceful failover, or graceful switch is when we want to actually go back to our original site after a failure. In this case, we may want to just temporarily go over to a site for site maintenance and then return back immediately after the site maintenance was done. And likewise, we want to maintain workload configuration states so we don't have a single point of failure for this solution as well. So if we go to the next chart, this kind of just depicts how graceful workload movement works with Lifeline. And in this case here, we no longer have controllers. We don't have these standalone LPARs because we really don't, that's only part of the GDPS Active solution. What we really have here is we have a 4 LPAR sysplex in Site 1 and a 4 LPAR sysplex in Site 2. We have Lifeline Advisor running in both of them, and essentially the second one in Site 2 is a backup, so that if Site 1 were to, if you bring down Site 1, the entire Site 1, you can still fail over and use the Lifeline Advisor in Site 2. You also notice we have Lifeline agents running on every LPAR, and on at least one LPAR, you have database replication, capturing database updates and sending them over. So prior to a planned outage, what do we have? The advisor notifies the load balancers that site, in this example here, we're going to say the workload is active in Site 1. So Site 1 is where all the workload updates happen. So that means any clients connecting in go through the first-tier load balancer, and in our case here, our second-tier load balancer will typically be a sysplex distributor, and that's from a lot of the customers we've been working with, that's typically what they use as their second tier. And so the first tier then selects Site 1 for all these connections coming in from clients, goes to sysplex distributor, and it will determine which LPAR is best able to handle this workload connection request. Database updates then, from flow 3, database updates are captured on Site 1, sent over to Site 2 where they get applied to the database over there. So what we're doing basically now is making sure that there's an alternate copy of the data on Site 2. Now suppose for some reason you want to bring down your workload applications on Site 1 because maybe you need to upgrade your applications. So in that case, what we need to do is initiate a graceful movement of this workload that is using those workload applications over to Site 2. So the first thing we do is we actually notify the load balancers to stop new connections. Existing connections will still flow to the workload application. So if you have any persistent connections where you may flow a bunch of transactions, they'll continue to flow over to Site 1. But any new client connections will no longer be able to, will be blocked by the load balancer. The next step is the advisor goes off and talks to every agent in this site and says, reset any persistent connections or drop the active connections for this workload. So that will now, at that point, once we've dropped all those workload connections, we know no new data is being, or no new transactions are being sent to this site. What we need to do at this point is we typically will wait a little bit of time until, if there's any outstanding transactions that were committed on Site 1 but not yet made it over to Site 2, we'll allow that to happen. Typically, software-based replication is no more than 1 or 2 seconds behind. So after a second or two, pretty much all the data that is, we're pretty much guaranteed that any data updates that occurred in Site 1 are now over in Site 2. What this means now is, because the term graceful, that really means we have no data loss. So every update that was done to database 1 is now applied over to database 2. And we can guarantee that no more updates are happening because we've told the first tier load balancer to not send any new connection requests in, and we told all of the agents to break any existing connections. So now we know there is no transactions for this workload flowing into Site 1. At that point, now the advisor can notify the load balancers that there's a new active site for this workload, and it's Site 2. So the load balancer now, clients may have been trying to reconnect, and either they timed out or hopefully they kept retrying, and eventually by the time before their retry timeout occurred, the first tier load balancer was notified that Site 2 is now the active site, and he can now send over to the distributor on Site 2. And it will distribute between the workload instances that are running in Site 2. So the key thing here is from a client perspective, they might have had a little bit of delay. They might have had a temporary timeout when they try to access a site. But eventually that will come through. They'll be able to actually go through to the second site where the data is the exact same replica of Site 1. And finally, now database replication goes the opposite direction. We now send any updates that occur in Site 2 get over to Site 1. So that the intent is that after, if you had needed to apply upgrades to your workload applications on Site 1, after that has occurred, you can bring those workload applications up and now do the exact same sequence of events to move from Site 2 over to Site 1. So what that does, and we've actually had customers that have done this, and they used to actually suffer about a 6 to 8 hour outage while they were upgrading their applications. With this graceful movement, they've been able to reduce their outage to about 20 minutes. Basically, they have an outage for 10 minutes while they try to move the workload over to Site 2, and then they have another outage of about 10 minutes when they move it back to Site 1. So it does give them quite a reduction in their planned outage time. Okay. What I'm going to do now is we're just going to go into a little bit more detail about what I've been talking about on the charts. And we'll go through these a little bit quick, but a lot of them is for your reference as well. But just to get a little bit more detail about what I was talking about on the continuous availability chart. So what the advisor does is, as I mentioned, it provides distribution recommendations to 2 tiers of load balancers. And what these recommendations are, there's several different types of recommendations, and we'll get to those on the next slide. But for the first tier load balancers, the advisor gives site recommendations. It basically tells the first tier load balancer which site to send requests to. And that first tier load balancer then sends those requests to a second tier load balancer. And I mentioned here's a list of vendor load balancers that currently support SASP. And for active standby, the site selection is determined where the workload is currently active. So as I mentioned previously, for active standby workloads, we guarantee that only one site is ever able to get connection requests for a workload. We do that using SASP by basically telling the load balancer the only place you can route requests to is to Site 1 or to Site 2, depending on where the workload is active. Lifeline Advisor also can provide recommendations to the second tier load balancers, assuming the second tier load balancer is also a SASP-enabled load balancer. And what it does there, it doesn't, since it's within a site, it now gives a different type of recommendation. It basically gives server-specific server application recommendations to say to the second-tier load balancer which server is best able to handle this new connection request within this site. Now, as I mentioned too, Sysplex distributor may assume the role of second-tier load balancer, in which case the Lifeline Advisor does not provide any recommendations to it. How does the advisor get these recommendations? It gets it from the agents, and the agents actually report 2 different pieces of information. The first piece of information the agents report is something called a WLM weight, or the workload manager weight. This is a server-specific WLM recommendation. What I mean by that is it's the how much displaceable capacity is available on the target system. With WLM, you can actually give priorities or class-specific classifications for workloads or for applications. So what server-specific WLM gives us the ability, so for example, if an LPAR is at 100% busy, but the server that we're running, that's running this workload is at a higher priority than most of the work that's currently consuming that LPAR, that other work can get displaced. So even though it may be at 100% busy, maybe 80% of it is lower priority work that can get displaced if we send new connection requests to it. So we actually take into that account to figure out how much displaceable capacity is available. Now, if there's zero capacity available on that LPAR, then the agent actually will tell the advisor, do not send any connection requests to this LPAR, because if you send it, we don't have enough capacity to even process the transaction. The other piece of information agents return to the advisor is a communication server wait. And in this case here, essentially what it is it's a measure of how healthy the TCP/IP stack is. So, for example, if TCP/IP is having some type of resource contention, either memory or some other type of contention, the agent can be notified of that, and it will return that information back to the advisor. It also will actually monitor the application itself, and what it does is it will actually look at the server instance itself. So, for example, if a server looks like it's up and running, but it is not accepting new connections, the agent monitors the backlog, the connection backlog of that server, so that if it notices that the backlog is growing, it indicates that that server can't keep up. So rather than have that server get completely overrun, the agent can report back to the advisor and say, stop sending too many requests here. You may have to reduce how many you send because you're sending too many to my server application. It can't keep up. So we kind of proactively react to servers that either are stalled or are maybe not as healthy as they should be or can't keep up. And so what the advisor does is he uses the relative weights of all these server applications that the agents provided this information back, and then he can use that to determine whether the workload is available or healthy within a site. So even though all the servers may be up, if there's no capacity on any LPAR in that site, or if all the servers are unhealthy, they may be all deadlocked or something wrong with those servers even though they're up and running, we could declare a workload failure in that case and want to switch the workload over to the other site where maybe the servers are working better. Going on then, the other thing that the advisor provides is the ability to group different server applications into workload. Early on in this presentation, I gave a definition of what a workload is, and what it really boils down to is if different servers all access the exact same piece of data within a database, for example, the same table, they belong in the same workload. So typically the way load balancers work is you actually just give it a pool of servers, instances, and the load balances between those like server instances. Since a workload can consist of servers that are completely unlike each other, for example, you may have a CICS workload that updates DB2 as well as a WAS workload that updates DB2. And in this case, both the WAS workload and the CICS workload would belong in the same workload group. So the advisor actually can group these different types of servers into a single workload and monitors those different types of servers and can declare workload failures depending on the availability of each of those types of server applications. The other thing the advisor is responsible for is detecting workload failures. And the way it does that is monitors the capacity of the LPARs within the active site for that workload, as well as the availability and health of all the server applications that make up that workload in the site. And it has the ability to dynamically switch that workload from the alternate site to the alternate site after it detects a workload failure. Likewise, the advisor also is responsible for detecting site failures. These are two different things. Since you could have multiple workloads running on a site, maybe only one of the workloads were to fail, so we need to monitor things on a workload basis. But if the entire site were to fail and you had multiple workloads running on that site, then the advisor is responsible for moving all those workloads over to the alternate site. And as I had mentioned previously in the figure of the Lifeline environment, the advisor communicates directly with the support elements over an HMC network to verify LPAR status to determine whether there's a site failure or not. Going on to slide 30, the advisor communicates also with a peer advisor, and the reason for that, as I mentioned, we do not want a single point of failure. It shares information about the workload state to the peer advisor, because a workload can be inactive or it could be active to a specific site. and the peer advisor takes over responsibility in the event of a primary advisor failure. The other thing that the peer advisor does is there's actually a way to gracefully take over the primary advisor as well. So, for example, if you wanted to apply maintenance on the primary advisor, from the peer advisor, you could actually gracefully take over the role of primary to allow you to take down the old primary to apply maintenance and then bring it back up. So it's not only during during a disaster where the peer advisor could take over, it is also you could do it gracefully. The other piece of information, or the other thing that the advisor does, is provide the graceful movement of a workload to an alternate site. This is a planned failure. So as I mentioned, part of the process is you prevent new connections from being distributed to the active site, terminate any existing ones, and reroute new transactions to an alternate site. Also mentioned previously, the advisor has the ability to modify or add workloads on the fly, so you don't have to change a configuration and then recycle the advisor to pick it up. Finally, the advisor provides an NMI interface so that network management agents can retrieve all this information. There's a lot of information the advisor has about the state of the workloads, all the different types of servers that make up those workloads, all the LPARs and that make up each of the sites. All that information is passed back, and so it's graphed pictorially to easier digest it. Finally, as part of when the agents are checking the health of all these of the TCP/IP stack as well as the server applications, it actually uses documented interfaces to retrieve this information from the TCP/IP stack. Slide 32, Workload Lifeline role and graceful switch. A key requirement is that updates to the database can only occur on one site at a time. So Lifeline is responsible for orchestrating the workload movement to basically make sure that workload connections are only ever directed to one site at a time. That is the active site. So prior to a planned outage, all workload connections are directed to a single site, and you can do this. The key thing with this graceful switch is all of these things need to be operator initiated. Unlike with disaster recovery, a lot of that could be automated or automatically done by the advisor. In this case here, it all needs to be manually done because it's really at the discretion of the operator at what point they want to fail over. So the first thing it's done is all workloads get directed to a site. This is accomplished being a modify command against a Lifeline advisor. To facilitate the graceful movement, basically workload connections must be stopped. New workload connections must be stopped. Again, a modify command against the advisor. You wait a period of time to allow any outstanding transactions on existing workload connections to complete. Next, you actually will issue a modify command to force a resetting of any of these connections that did not complete in a timely manner. And then you can actually redirect all the new workload connections to the alternate site, again via a modify command against the advisor. Going into then on slide 33, this will what I wanted to talk about here was just a couple of key display commands and a couple of key modify commands against the advisor. All of this display information, all of this information is also passed through to NetView through our NMI, where NetView can actually pictorially graph all this information on their Tivoli Enterprise portal. But you can also get all this information via the displays. So I'm just going to quickly go through on this first one is actually just the advisor detail command. It basically says all the agents and all the load balancers that are connected to this advisor. The display config basically tells you the current active configuration for the advisor. The LB detail, as part of SASP, you actually register, they're called registering load balancer groups to the load balancer, and then it passes that information over to the advisor. Well, rather than having to log on to the load balancer and display all this information, we can display this information directly from the advisor. Finally, the last one is a workload detail display. This basically says what is the status of all the workloads. Are they active? And if they're active, which site are they active on? And what is the status of all the server applications that make up the workload? Go to slide 35. This is just an example of an advisor display. As you can see, the first line on it is what is the role of the advisor? Because we always have a primary advisor and we always have a secondary advisor. So in this case, this is the primary advisor. He has a set of load balancers. One of them is a Tier 1 load balancer and one is a Tier 2 load balancer that is currently connected to him. and he has a set of agents, Lifeline agents, that are also connected to him, and we indicate which system and which site that they reside on. And finally, the last line is the peer advisor. This is a secondary advisor and where it resides. The next display on page 36 is the workload detail display. This is probably the most common one that you would use. This basically tells you in one snapshot the status of all the workloads. In this case here, I have two workloads. I have workload 1 and I have workload 2. Workload 1 is active on site Plex 2, and there's 4 servers that make up that workload. There's one on System 1 in Plex 1, and one in System 3 on Sysplex 2, one on System 2 in Sysplex 1, but if you notice, there's also one, but it's now no longer available on System 4. So, for example, since we're active on Plex 2, if we were to lose the other server on Plex 2, where it went from status of available to unavailable, we would declare a workload failure for workload 1. And then down below is another workload, workload 2, where there's 2 servers that make up that workload. Some of the key advisor state change information are state change commands that I wanted to highlight. The first one is an activate command. As I mentioned, part of directing a load balancer to say which site a workload is current, to direct all workload connections to, how that is done is via this modify activate command. From there, we basically say which workload we want to activate and which site we want to send it to. So once that command is issued, the advisor goes out to the first tier load balancers and says, any connections for this workload go now to the site that was specified on this site command, on this activate command. There's also a deactivate command, and that is for a workload. And what that is used for is, as I mentioned, there may be persistent connections that transactions can still flow over. We need the ability to actually go out to the agents and actually reset each one of those. This deactivate command does it. So when we do a deactivate command for a workload, the advisor goes to every agent in the site where the workload was last active, and it resets any existing connections. There's also a quiesce command, and that's really what that does is it tells the advisor, go off to the first tier load balancer and say, stop distributing any new connections for the workload. There's also a refresh command. This is so that if you dynamically want to add or alter workload different definitions in your configuration file, you can do that and then do this refresh command, and will automatically pick up the new changes. And finally, I had mentioned that as part of the peer advisor, it can either do a takeover during a disaster where we lose the primary advisor, or it can do a graceful takeover of the peer advisor. And in the takeover command will do this graceful movement of the primary advisor from the remote peer to the local advisor who issued this takeover command. A couple of quick agent display commands, similar ones. You have a display config and the display members. I'll show you a display members display on the next slide, 39. Essentially what this is all of the servers that the agent is monitoring. So it basically is monitoring all these different servers, and all of this information gets passed back to the advisor, and the advisor reads this information to figure out what servers are available for what workloads. So in this case here, we have 4 different servers that this agent is monitoring. But it's, again, a very quick snapshot to figure out specifically what the agent is monitoring on behalf of a specific workload. A couple other quick commands, and then I think we'll run out of time. But basically, we have also state change commands for agents as well. There's 2 of them here. Similar, if you're familiar with Sysplex, where you can resume and quiesce target applications. So, for example, with Sysplex Distributor, if you have 4 targets and you want to bring one of those targets down, you can quiesce that target so Sysplex Distributor no longer goes to that specific target. A similar thing exists for this agent enable and quiesce. If we're using SAS-P to influence a second-tier load balancer, using this enable and quiesce command will allow you to also do similar stuff that quiesce and resume does for Sysplex Distributor targets. The other thing is debugging. There's a lot of debugging information that we keep, and it gets recorded in syslog. So it's enabled on startup via debug level statement in both the advisor and the agent, and you can automatically change it dynamically change it on the fly as well, so that we actually trace a lot of information. We do not use ctrace for this product. It's all syslog debug information. I'm going to skip the next few charts, and I just want to jump. That is more for your information. It's just a little bit more detail about the flows. But since we're out of time, what I wanted to do is just jump to this last chart. We actually have a website out there for Multi-site Workload Lifeline to give you a little bit more information about it, as well as our documentation, our user guide for this product is also out there.